Welcome to another episode of Robo Papers. Very happy today to have Arthur and Hongsuk, authors of this paper called VideoMimic. Basically, video imitation enables contextual humanoid control. Right, I'm glad to have both of you. Maybe as a start, maybe Arthur, you can start first, share a little bit about yourself, your background, and then Hongsuk as well.
Yeah, I'm Arthur. I'm a PhD student here at UC Berkeley, and my research interests mostly focus around robotics and specifically how we can enable general robots to interact in the real world. So that is, I work on everything from like locomotion, which this paper more is, to manipulation and different approaches to that. So I guess that's a bit about myself.
Hi, I'm Hongsuk. I'm also a PhD student in Berkeley, advised by Angju and Jitendra. And now I'm more working on robotics, like trying to make like computer vision output useful for robotics and more focusing on like RL stuff.
Yeah, so maybe as a start, Arthur, if you can maybe share screen and then you can, can give us an overview, maybe some motivation behind the work.
Yeah. I guess maybe I'll just play the video briefly first. So basically our goal in this work was to have policies for humanoid robots that can kind of do terrain traversal and interact with the different objects in the real world with their whole body. So the main skills that we end up focusing on are this like stair climbing and terrain locomotion and sitting and standing type behaviors. And the way we did this was kind of different from a lot of other works. So the traditional approach to learning humanoid locomotion or kind of legged locomotion in general relies on kind of manually tuned reward functions, and it's quite a labor-intensive process. What we want to do was see, can we just learn by watching or just learn from human data? So you can see here we can basically take a video of people and then turn that into a format that the robot can learn from. And then we basically take all of those demonstrations and distill it down into one policy. So that's the overall, I guess, idea and goal of this work. Obviously, there's like a lot of individual details, but that's like at a high level. And you can see kind of here what we're able to achieve out of that. Yeah.
Yeah, really cool. Could you tell us a little bit about how do you do it?
Yeah. So I guess maybe the best way to like go through that is to kind of show the different aspects of the pipeline. I guess recently there's been kind of like, and Hongsuk can also talk more about this, but there's been a very rapid progress in the ability to take like basically straight RGB monocular videos, so from one camera, no like multiple cameras or stereo or anything, and turn that into a point cloud over time. So you can basically, take just any video, and for each like basically pixel in that image, you can get the 3D position of it in some world frame. So you're like kind of jointly estimating both the camera motion and the scene geometry. And I guess this has kind of been a long-standing problem in computer vision, but recently kind of by scaling data, there's been like a rapid, I guess, improvement in this with work such as Duster and more recently stuff like Monster, Megasam, VGDT, even more recent, I guess. I think you had the author of that on the podcast also at some point. But yeah, so that's kind of the background. Hongsuk had like a work which was using outputs from Duster to estimate human position that you basically have. He can talk more about it, but like once you have this kind of 3D scene geometry, you can then work out how like a human fits into that. And once you have like the human in the scene, I guess, our work kind of extended that to human over time. And then we kind of remap that to a robot. And from that robot motion, we can then in a simulator learn actions, which are then, I guess, deployable in a robot. So that's kind of the like high level picture, and you can see the kind of different stages of this. So for example, you have me walking up and down this like staircase here, and then you can see this is kind of the estimate of like the human's motion, which is then turned into a robot motion, which we then are able to kind of learn a physical trajectory from.
Yeah, to add some little more like context of the history. So like many of the like human pose estimation literature have been like focusing on like only getting the like local poses of human. And some papers worked on like getting the location of human recently, but they didn't really focus on getting the scene together, which could be like transferred into the simulator, so we can do contextual imitation learning. So I think like this paper is not only actually showing the like usefulness of like reconstruction, but also like kind of showing that we need a scene together with a human so that it can be transferred into the simulator.
Yeah, so I guess a real to sim, then back to real kind of approach right here.
Mhm.
Maybe like I have a quick question. Maybe you brief into it like a bit more detail later, but I'm just curious, like what if the human do something that, let's say in this particular case, the Unity G1 can't physically do, you know, what happens then?
So I think like that's like there's like I guess an aspect of dataset curation. So like if there's something it can't do, like it can't do it, and like that's something you probably shouldn't include in your dataset. In practice, even if it fails on emotion, it's not like a huge issue. Like it just doesn't learn it in the simulator, and then it's fine. Like either you just have bad retargeting, or even if the retargeting is good, if it's like physically impossible, then it probably won't be able to do in the simulator. Like, yeah, I guess it's a limitation, but it's like only a limitation of the hardware. It doesn't really constrain the method that much, I'd say.
Got it.
We also do like something interesting, I think. So we do have like retargeting, which like reduces the embodiment gap. So we can like get the like physically plausible target for imitation learning. But also we, while we are reconstructing the scene, we actually like reduce the scene to the like G1 size, so actually it can do its like actions. So if there's two big steps on the reconstruction that like Arthur is tall, so Arthur can do it, but like G1 is very small, so but he
Yeah.
cannot do it.
Yeah, that's what I
Then
thought.
we like reduce the size of the stairs like because
Yeah.
but it's not manual, it's like all automatic. Like we have this kind of simple like mesh, the yellow mesh here, but that we reconstructed as the G1 size, not like Arthur's size. So by doing so, we can scale the whole scene into G1 size, which makes the whole motion like physically feasible.
But doesn't that have ramifications for when you want to use it in the real world? So how do you test it then?
Basically via like a generalization approach, right? Because I guess as we might get into, we have this like multi-stage approach where at the first stage you're doing tracking, but by the end, you learn like a generalist policy. And so basically once you can generalize different, let's say, stair heights or whatever, it's not an issue in practice because you just kind of learn pick the skill that is appropriate for the real world size.
Gotcha. So this would probably be a problem if you had just one staircase, but how many I guess examples did you ended up in your data set for that task?
So actually there's around 120 individual clips in the dataset. I don't remember off the top of my head how many are on stairs per se, but
sure, yeah,
it's not like an extreme number, but it seems to generalize reasonably well.
Yeah, I guess 120 actually isn't that much, and especially given how easy it is for you guys to collect data, that's probably what, like half an hour total, maybe? I don't know.
Yeah, although I guess as we'll probably get into later, like there's still a long way to go. So we have a fairly high like failure rate or like rejection rate of videos, just because like reconstruction of those things might fail. So yeah, it's a bit more than that, but it's not like crazy. Like yeah.
Constraints then on like what kind of video, or I guess what's next? If you want to get to this later, but like what are the constraints on what kind of videos can I include if I use this?
So I think that in practice, when you record videos with your like phone, like just of people, it works reasonably well. We tried also like scraping internet data and using that. And when you don't have like as much control over what kind of data is going in, that's when it really starts to fail at a much higher rate.
Gotcha.
Yeah, and I guess also, I guess there's some scenarios on which like I'm like obviously the 3D backbones are also still not perfect, and so that's another case where like if you're on certain scenes, for example, which have less texture, it might be difficult for it to reconstruct.
Gotcha.
Yeah, that kind of thing.
So I would guess that like say so you said that internet web scale scraping didn't work so well. So like scene change is obviously going to cause it to fail. Scenes without lots of
or, like,
overlap
different
for
like
the
filter
camera.
lengths,
Okay.
or like if people are adding
Yeah.
like crazy filters on the video that are just OD
Sure.
for
Lots of dynamic scenes. How well does it handle like really dynamic like walking in a crowd, for example?
maybe Hongsuk.
Yeah, so to add, like I think it fairly works well, but the bottleneck is on the like point cloud to meshification. So even if the point cloud is like we think it's okay, but like when it comes to meshification, there could be whole spike and some like ramp, like smoothing out the high frequency detail of the geometry and so on. That was like most bottleneck I think for the real to sim part hindered us from using internet data. And about the dynamic scene, so I'm not sure if we are gonna talk about like whole method detail, but different from my previous work, which was presented in CVPR, I used kind of like different strategy to get the human location in the world. I guess everyone knows like Duster and Monster. So like Duster, Monster, and Megasim like outputs the dynamic point clouds together with a static point cloud. And like here, like dynamic point cloud is human point cloud. So in a nutshell, we are trying to align the human mesh, like local human mesh poses into the dynamic point cloud, giving some kind of L1 loss between them. But those methods like Megasam monsters outputs like dynamic point clouds become very messy when there are dynamic motion, which means if human is jumping across stepstones, the human point cloud like translates in Z direction. And then like, of course, that motion becomes very messy. So if that's like not like harsh enough, I was able to regularize it with like some kind of like prior and like smoothing the temporal motion. But I think if it's like some kind of parkour over the rooftops, it could be very noisy and not usable.
Yeah. Well, maybe this if we can take a step back, if you guys can walk us through like kind of the whole like setup. I know you guys started with some mocap pre-training, right? So if you guys can kind of talk us through, give us the overview of the whole setup. Yep.
So I guess I guess maybe we can talk through the entire pipeline from like the from video, and then we can go to like the robotics part. Does that make sense? Yeah. Hongsuk, do you want to go through the vision stuff?
Yeah, sure.
So you can.
So the real to sim part like setup is that we collect videos of human demonstrating like some kind of leg skills in the wild with our iPhone. So input is a monocular video input. And from those videos, we reconstruct the whole scene of human and the static environment. So the human is represented as like SMPL body model. But here we don't use mesh. Like this is just for visualization. We actually use like just the joint angles and like joint key points. And the like scene is represented as like point map from the like deep visual slam. We mainly use Megasem, and when it fails, like due to like textureless scenes, we use Monster. And here we have like 2D pose detection. Actually, this is like not used in the final output, but used for aligning the two representations, SMPL body model bodies and the like scene point maps. So what we do, I mean, I have some slides for this, but what we do is basically, as I said, like align in the like local simple meshes that like global transformation with the scene environment point maps. But here, like simple provides scale information, which like slam reconstruction lacks, and slam and the dynamic point clouds give the information about the human's location. So they are like co-aligned and helping each other. And the way we are doing this is using the 2D pose detection. So we can lift the 2D pose detection to the dynamic point cloud of the slam by the pixel aligned depth of the key points. So by doing so, we have like 2.5D lifted key points from 2D pose detection, and we're actually giving L1 loss between this lifted key points and the like simple key points. If it doesn't make sense, please give me any questions.
So to be clear, I guess what happens is like you need to know where the corresponding like 2D point in the images that you get from the vision from the like 3Dification, and then you align those in 3D.
So the 3D, so let me go through this just because this is a fairly complicated process, I guess. So the 3Dification gives you like takes your video, turns it to a point cloud, so it's 4D, right? So I have three XYZ in time for my scene, but then now you have to use SMPL motion reconstruction pulse out gives you the human model. I don't actually fully follow why you also need the 2D pose estimation.
It's because you need to know for a certain like 3D point in the point cloud reconstruction, you want to know which joint in the SMPL that corresponds to, basically.
Yeah.
Okay.
Yeah.
You want to know that this is an elbow and that my SMPL elbow should be in this 3D location.
Got it. Okay. So like the actual joint identification is happening in 2D at each frame, and then you project it into this.
Correct.
Okay.
The
Exactly.
like basically the like the like SMPL 3D thing might not be like perfectly aligned as to the to the 3Dification that's just going based on the video and not considering the human explicitly.
I see. So basically the step in that step there is just too noisy, and so to get a really good one, then you need to do this. Is that the idea?
You want it to be anchored to the same point cloud, basically.
Okay. Makes sense.
Yeah, so like 2D pose detection is basically giving the correspondence between the SLAM point cloud and the SMPL body model. Yeah, so this is real time, really fast. Like the optimization happens in like 20 milliseconds for 300 frames with A100 GPU, 100 GPU. We use like second order optimization implemented in JAX. Yeah, it's pretty fast.
You have your own. Sorry, this is the optimization for the SLAM step 2. So, yeah.
Oh yeah, this kind of simple and SLAM point cloud alignment is done in optimization.
Yeah.
And then once we have this, like we don't want the like simple, so we retarget this like simple joint angles and joint key points to the G1 humanoids using hierarchy, which is also like optimization, like JAX optimization in second order. And then so these like retargeted humanoid key points become the imitation target, but we also need the like paired environment mesh so that it can give actually like physically plausible, like learn something physically plausible. So we like meshify the point clouds to mesh with like state-of-the-art meshification methods. We try like neural draw contouring, but I guess these are all similar methods doing the meshification in a neural network way. And then we are actually doing like calibration, which is like gravity alignment. If we don't do this, like it doesn't align with the gravity. If we just put naively into the simulator, it could be like slanted or something that doesn't make sense. So we calibrate it with like gravity estimation.
That makes sense. So I'm curious why use the like if you have an iPhone, why not use like the point clouds that come out of that? Like, because that actually natively records 4D video, right?
I mean, I think it's a like great idea. Like all iPhones have LiDAR. LiDAR like is kind of very sparse, like just 11 by 11 in iPhone 15. So
okay, yeah.
The quality of depths might be not as good as Deep Visual SLAM for the human point clouds.
That might be true.
I think it's worth trying it. Yeah, I'm not against it.
Yeah, I mean, I'm curious. It does give you, even though it's low resolution, it actually does give very good quality depth, at least for mapping. But maybe you're right that it's just not sufficient for this.
I think it's actually pretty like reasonable. I think basically, our pipeline has like a lot of components, and some of them could easily be swapped out, right? So we don't really care if it's a monocular video input or like other method like Megasam, which is like doing this like visual slam approach of these things. Like you could easily, all you need is like basically depth at every frame plus camera poses, and whatever way you get that, whether it's like how we're doing it with these kind of purely monocular methods, or whether it's using some, you know, other approaches based on LiDAR, or you could even imagine using something like Z camera or something. Yeah, like I think like in terms of the potential scalability, doing it from monocular is maybe the most interesting. In terms, if you want to like scale it in the most reliable way, maybe you want some other input method, but it doesn't really matter for the rest of our pipeline.
Sure. Yeah.
in that way.
Yeah, I'm just curious as to how many errors come in from the
Yeah.
depth quality, basically.
Yeah, yeah.
Okay, so as the more roboticist person than a vision person, I was like, okay, when I see the actual the other part, like I understand. I don't want to.
Yeah.
It's like, okay, I can understand how that would work. This part actually is like, I'm really shocked that you can get good videos just from like record and like actually create this full 3D scene with like kinematic retargeting. Blown away by that. Like this part. So I mean, both obviously great work,
Yeah.
but you know what I mean. Yeah.
Yeah,
So
yeah.
there's, okay.
Sorry, can I ask a question? So again, I guess it's similar to the question earlier I asked, where I'm still trying to understand how do you go from, let's say, after your 2D pose detection, you know, you have a different form factor to and in this case, the Unitree robot. How do you do this kinematic retargeting?
So basically, like you have some like joints on the humanoid, and then you need to define some like, essentially you basically define like a mapping between, okay, this is the human's elbow, this is the robot's elbow, and then you perform like an optimization to basically make the humanoid pose mirror the human pose as closely as possible. And we also use some more like losses in our pipeline to try and like ensure that the humans like feet are like still close to in contact despite the scale difference in these sorts of things. But at a broad level, it's basically just you have like one skeleton and another skeleton, and you define some mapping between them, and then you basically optimize it such that the mapping is as close as possible. Yeah, that's the like basic idea.
I mean, I imagine like for certain poses where maybe more, let's say if it's a human that is doing, let's say, a jump, you know, like where the contact point is in a split second.
Yeah.
So I suppose for those more challenging ones, it's you will probably need really good like kind of retargeting, right? Do you see that like this step being a bottleneck, at least for this pipeline, when you're doing this kind of task where you're just walking around? Or
yeah, for some things it's a bottleneck, but I would say like you can get quite a lot of mileage out of this approach with some tuning. I mean, retargeting is a problem that's been like very extensively studied. Like we're not the first people to look at this. Like I don't think we would like claim that this part is like that novel. But yeah, like it is like just a lot of work, and admittedly like some amount of heuristics to make sure that it works even in those kind of situations.
Yeah, like just to add one more like context, I think in my experience, up to retargeting part works really well, even for a very diverse dynamic motion in YouTube videos. Like there's like crazy motion spinning or like jumping and parkour, and I've seen like the retargeted human emotion is pretty good. Like overall good, but as you said, like some kind of contact details are not accurate. But I assume like retargeting data doesn't have to be like 1 millimeter accurate, so it seemed to be okay. So this is pretty much like real to sim. So eventually, what we get is the like retargeted humanoid and like mesh in the 3D like walled frame, which is like compatible with the Isaac Gym. So we can do collision checking with the mesh, and also we can use the like humanoid joint kinematic, like action-free kinematic data to guide the like RL policy training. And then like this one is like, so I guess this is like showing the possibility of internet video data. So our courses, one of the courses, David put a lot of data, collecting internet data and like getting plausible data, but like we didn't end up using it. But yeah, we are showing that it's possible. And also the second thing, the right column is showing like kind of like versatility of our real to sim pipeline. It can handle multiple people in the scene. Of course, like multiple people's retargeting. And also like exciting thing is like eagle view rendering only from this reconstructed point cloud. I mean, like not many humanoid papers have been focused on like blind locomotion, but now we've gone forward by using the like LiDAR high map. But I guess the next step is like quite obvious, using RGBD eagle view input so that humanoids can like pre-plan the steps and semantically understand the world before taking actions. And this shows the feasibility of getting the data, because it has been not possible because all the methods were just using mocap data that doesn't have like any environment or images surrounding it. But with our real to sim pipeline, now we can collect the environment, and it shows it's like eagle view rendering is super easy from it. Like it takes like very short time, and yeah, I guess it could be our next work project too.
Yeah, got it. So I guess what you're saying is that like it's so this gets around the trouble of having the human like put a GoPro on his forehead, and if you can reconstruct this 4D scene, basically you get the eagle view, right? Is what you're saying. Okay.
Oh yeah, but I will guess. I forgot to tell the limitation. Limitation is that, of course, as you can see in here, there are like holes in the reconstruction which are invisible from like third person view. So like this kind of things could be like, I assume, handled by like generative models and paintings.
How about the, so in the right side of the screen here, we see that there's the depth map just ends where, and at the part where I guess where the video wasn't, right? So get handled. Does that matter? Does it not matter?
So I guess that like potentially does matter, right? So this is like definitely a limitation, is that potentially. So in our paper, we didn't not actually use like the direct depth or RGB rendering. We can do it, but we didn't use it as part of our policy input. But if you actually were using this data, then you would have to work out how to handle that. It might be that with enough scale, like it's in practice not that big of an issue, but it's likely will be an issue. And like there are multiple ways to handle it. Like one would be like if you just like basically kind of try and scan the scene a bit first with like by changing the camera angle a bit. Or you could do potentially multiple camera views or these sorts of things. Like there's obviously more to do here. This is not like the be all and end all, but it's just showing the potential of what you could do.
Yeah.
That definitely is a problem if you wanted to use this.
Okay.
Or you could use some like in painting methods, as Hongsuk mentioned, because if you're tracking the motion reference, like we're assuming that the video contains like information about the contact points that the human has with the environment. And so like the crucial stuff for physical simulation is there. And so the kind of stuff outside that is somewhat extraneous also. So in painting might work reasonably well.
Yeah. Yeah, I would imagine that in painting would actually work pretty well for these, just because for the reasons you said. That makes sense.
Yeah.
Okay. Cool. So do you want to move on to like how do you train it? What do you actually how do you make this work? Yeah.
Yeah. So basically I guess the input to our kind of like simulation pipeline is kind of something like you see on the left here. So like we have the robot kind of moving over time. It's a mesh rather than this like point cloud representation. So more like and so you basically have a sequence of kinematic poses over time, and your aim is to track it. So there's a relatively kind of tested technology at this point called VideoMimic, which was developed by Jason Peng. And a lot of works have kind of used this, and you can use it to get kind of on like humanoid robots, basically, of like tracking various motion references. So that's kind of what our pipeline is based on. So traditionally, most of the approaches have not considered doing stuff that is using data that has like an environmental context. So that's kind of a bit more of an extra challenge here for us. But anyway, before we train on our own data, we actually do like pre-training on mocap data. So that's basically data that's very clean, collected in like a mocap suit. And we basically learn to physically track that. So when I say tracking, like what does that mean? So the input is obviously just like a sequence of kinematic poses over time, which tells you kind of like where you want the robot to be, but it doesn't tell you how you need to actually actuate the motors in order to produce the same motion. And so that's basically what like the VideoMimic stuff does. So you start with these references and you define some reward function, which kind of tells you, okay, stay close to the reference. And then you track that with reinforcement learning to get kind of good action outputs, which tells you how to actuate the motors. So yeah, the first step of this is like mocap pre-training, as I mentioned. So this is not our own data, but it's easier to track. And so you can kind of learn generally how you achieve various poses on the robot. So each step you kind of give it the pose that it needs to get, and then we learn to track that. Then the second step basically takes the policy from the first step, and then we also inject a height map into it. And this is the first step where we actually use our own data. So we take, all the whatever 120 clips, and we train a policy to kind of track all of them simultaneously over the terrain. And the robot is also like told the kind of shape of the environment around it. So that's great, but it only works conditioned on the sequence of like whole body poses. So at each time step, the robot is told basically that it needs to be at a specific like full body pose, which is not deployable in the real world and like new scenarios, because you don't know, okay, for this new set of stairs, like what is the exact sequence of like gait and all this that you need to walk up that stairs. So that's why we then take all those references and then we distill it into a policy which no longer requires the full body input. So that's this like distillation with root condition, the third step. And then at the end, we do kind of another round of reinforcement learning to kind of dial in the behavior of that. So at the end, we're basically just left with a policy that you can kind of push the joystick in a particular direction. The robot kind of works out to do what to do based on the height map of what it sees around it. And yeah, where it's supposed to go.
Nice, makes sense.
Like basic pipeline. Yeah.
It's a lot of steps. I'm always.
Yes.
It's interesting how complex modern like RL pipelines end up being with all these different modules and fine tuning, different dicing. Yeah.
Mm-hmm.
Okay.
I think the overall like insight that I guess people have realized in the past like couple of years is that in order to get good policies, it's much easier to basically go based on like a tracking objective than a more traditional pure RL objective often. And the reason for that is you're basically shortcutting the exploration issue. So VideoMimic has this thing called reference state initialization. And all that means is that when you're trying to track a given motion, you initialize your RL episode from like randomly sampled initial conditions from within that. And that means that you quickly learn a very good like value function, which then means that you can learn to kind of stitch together all these individual pieces of the trajectory much faster than you necessarily potentially would with like RL from scratch.
Is there any concern that you'll get to a suboptimal solution when you do this kind of thing?
I guess in terms of like suboptimality or that kind of thing, it's possible that your reference is suboptimal. And so like, if you have really bad references, you won't end up with a good policy. So there's a certain amount of like data engineering that goes into it. But I think it's much easier to shape behavior via data than via reward engineering, which was like a more traditional
Absolutely.
approach. Now the disadvantage of tracking is also that you need to basically change the conditioning, because when you're initially learning to track references, you basically at every step have to condition it on like the exact position it should be in at that moment. Whereas with like a traditional RL thing, you basically just give it the overall goal. So at the end, your policy in a traditional pipeline would be like, you might just say, okay, go at this speed forward, and we'll do it. Whereas in DMimic, you're saying, okay, I want your leg to be in this position, your arm to be in this position. And you don't have access to that information at test time. So then you need another step where you kind of drop out that information. So that's why you kind of have this multi-stage pipeline.
And that's where your distillation comes in. Yeah.
Yes.
Well, sorry, remind me what the RL fine tuning part does. Why do you need a third step or fourth step, I guess?
Yeah. So basically it turns out.
Allshire, I think you can also like kind of explain more about the like root command using the light autometry we are using. That is not like root velocity command.
That's a good point. I guess first going back to like your question, Chris, is like basically what we found is like when you do distillation, the performance does not actually reach the same level as when you are conditioning on all the joints. I think it's probably because when you have like the full reference information, your policy can kind of cheat because it kind of can overfit to the to the motion given the like proprioception. So like, for example, if you're going upstairs and you can't see like the next stair afterwards yet, but you know like this is the exact like arm motion that it does when you're walking upstairs. You know, there's certain like stairs, it kind of will know ahead of time what it needs to do. Whereas when you drop out the like reference at each state, you might not have that information. I think that's partially what's going on. So then when you do like RL fine tuning, you kind of like remove that issue because you're like directly fitting on the observations that you have. I will note that for the RL fine tuning, like the reward is the exact same. So for all of these like stages, even though it's like 3-stage pipeline, we don't like really change or tune the reward like.
So it's always the deep mimic style like replication reward.
Yeah.
It's
So like
just about
the RL fine tuning is basically like, it's still like a data-driven objective. It's just not conditioned in that way. And yeah, going back to the conditioning, one interesting problem that we ran into in this work is that most locomotion pipelines use like a velocity condition. So you basically say, go at like this speed forward at this time. The problem for us when using that is like we have a terrain that we're going over. And so if we just say go in this direction, if we like deviate from the velocity during the trajectory, our like target will not be bringing us towards the reference, if that makes sense. So it kind of, and because like our objective is driven by like motion that's synchronized with the terrain, that is a problem. And so the solution that we have to that is instead of, so traditionally people would just like move the reference to wherever the character is, and that works when it's like flat terrain. But yeah, because we have an environment that doesn't work. So what we do instead is we basically condition on what we call like the root direction. So it's basically the like direction and distance to the reference motion. Even though this is not a velocity condition, in practice at test time, you can just use it in the same way. Where like you just basically directly on the joystick input, use that to set like where it thinks the reference is relative to the robot, if that makes sense. It's like if you push the joystick forward, like a certain amount, it might say to the robot, okay, like the reference is 0.5 meters ahead of you, and then it starts to move in that way, if that makes sense.
Why is this better than like using a root velocity?
Oh, it's not necessarily better, but root velocity would not work in the case where you need the motion kind of synced with the terrain, if that makes sense.
Yeah, okay.
Yeah.
Then when you want to try to actually use this, so for example, push the thumbstick forward, and then it projects it along the terrain 0.5 meter or whatever it might be, so that it's actually like synced with the Z height as well. And that makes sense. Okay.
Yeah.
Oh, sorry. It's not like the command is not like synced with the height at all. It's just like it's just a different like formulation. It's not like an environment aware command. But at the training time, that is the error to your reference. But at test time, you just use it in the same way as a normal joystick command.
Okay, gotcha.
I guess one like core like thing of this like implementation is that we are like tracking the global location of the humanoid in the environments, and we are keep like localizing the G1's location in the global environment, and then keep like giving the error feedback to the control policy so that it can like close the loop between the like command and so it's kind of like avoiding the like error accumulation.
Yeah. Then one of the nice things about this formulation is that we basically learn the kind of relationship between like these kind of how the humanoid is moving and how it should move relative to the environment, like quite naturally. So for example, I note that like in these cases, like when we're, let's say, if I scroll up, like when we're like sitting and standing, you don't need to like explicitly tell the robot to sit or stand. That just like emerges from the data. So like when you pull the joystick back and the robot is like kind of back towards a chair or something, it knows that it has to like sit because there's like a high position, its height map behind it, and it's seeing that in the data when it's like moving backwards towards the chair, it needs to sit. And then again, when you push the stick forward, the same thing, it knows it needs to stand from that position. So that's like one nice thing about this, like I guess dropping out of the conditioning with this kind of data.
It's a very intuitive way to control the robot. That's nice.
Yeah.
Are there cases where that doesn't work? Like what if there's multiple affordances, like I guess like parkouring over a bench versus sitting on it or something like that?
Yeah, so in some of those cases you might need to have some more explicit conditioning.
Gotcha. Okay.
I guess we didn't have that issue in our case, but yeah. I guess that gets into kind of more big picture questions about like, oh, do you need language conditioning or etc. But yeah, for us, we weren't really considering that.
Yeah, I'm curious, especially for the case where the humanoid is kind of going backwards and sit down on the bench. In your like 100 or so videos, right? Was it like you have some videos where you actually also the human also walk backwards towards the bench, or it actually start with sitting on a bench and then standing up to go forward, and then somehow the model learns how to walk backwards? So which?
So we had like some videos where it was like the human is going backwards, also like some like going backwards like downstairs or these different things. So there was quite a few different scenarios.
Yeah, but I don't think we had like a continuous motion of going backward and sitting on a bench, but like we have like chunk of each atom motion.
Yeah.
Interesting. So you do have videos walking backwards, but you don't specifically have a video of walking backwards and then sitting on a bench. But somehow this model, okay, really cool.
Can I ask about this video in the top center? Sorry, finish this thought, then I'll ask.
But yeah, I guess like you have these like cases like for example here where it's like the person is going back and then turning around, but yeah, I don't know, like any exact motion is probably not in the data set to that level of precision, right? But like I guess RL sees a lot of states and then it's pretty robust at the end. Yeah.
It's interesting to me, that you have these videos with, when you're actually testing it in the real world, you're doing basically just directional control, like moving the robot around, interacting with stuff. But you have a lot of these motions, like the guy doing Tai Chi or something in the middle there. And this one above, which is really strange, the one where there's a person, like that's a person doing hockey, like sliding across the ground. How is the robot supposed to reproduce that?
I think these motions were, Hongsuk, correct me if I'm wrong, but these ones were not in the data set that we used.
That makes more sense.
So some of these are like, this is kind of showing off the like 3D reconstruction capabilities. This page, it's like not. A lot of these videos are included, but like this one, I think were definitely included. But like, yeah, these ones are not in the dataset, at least these. So yeah, and this,
Okay,
yeah,
that answers that.
this one I actually tried to train on the like green background, and it can jump down, but the G1's arms are not strong enough to do that kind of get up motion, which is sad. But maybe
is sad.
eventually someone can.
That
Someone
would have
can,
been very cool. One of the words. Yeah.
yeah, for sure. Maybe the next generation of humanoid hardware.
I mean, it strikes me that actually the amount of video data you use is very minimal. It's like just over 100 clips.
Yeah.
And so would it be fair for me to say that this research doesn't so-called show, I mean, because like there's one school of thought where, oh, there's so much human video out there, you can script the entire YouTube and get the scale that way. But it seems that maybe your research here it's not necessarily that, it's more that, like you can actually learn very effectively just from not that many video and get this really performant, I guess, scene aware or like obstacle aware policy.
So I wouldn't say the point of our like work is to show per se that the minimal amount of data is good. It's also not to say that our approach is scaled either. I think philosophically, it's nice that we can do things from like this RGB video, but in order to truly prove it, yeah, you'd ideally want like many thousands or millions of videos. However, I think the thing that we're showing is just that this data is like available at all, because previously there were very few data sets and like no kind of general in the wild methods that give you this kind of human motion with environment. And that like, we show that it can work for robotics. Like previously, all of this kind of terrain locomotion in the world has been based on like manual reward engineering and manual scene engineering. And so we're just trying to show that like a data-driven approach can work for this. And yeah, potentially scaling needs to be left for like a later date or another work. Yeah, so I don't think we're claiming that like,
I think like I want to kind of make a bold statement. If you're given the same amount of money that the companies are spending on the teleoperation, we could scale up the data hundreds and thousands more and then like get much more generalizable human-like task, like human-like motion on diverse tasks. So, I mean, we just like spend like 2 days to collect these data, like spend like a week to like get the reconstruction, but we know how to do this and we have the pipeline and we have the money to do it. I think it's much more scalable than like the existing like paradigm.
Yeah, I was just gonna say like if you like, I mean, there are a lot of work like ongoing by different groups that are looking to do whole body teleoperation. There are a bunch of papers that we actually interview on this podcast, and those are all very cool. But yeah, I mean, it's first of all, it's extremely hard to do those well. They all have many different trade-offs. Whereas you guys just take like maybe just 100 videos. It was so easy, man.
So I'd say our work is not necessarily like trying to compete with whole body teleoperation papers, because the kind of tasks that we're doing are pretty different. You can't teleoperate a humanoid to go up a stairs unless it's been like trained in simulation to go up a stairs. Most of the whole body teleop works are mostly focused on, can we, let's say synchronize upper body and lower body motion. But fundamentally, they're kind of focused on this like flat ground case and like learning a controller that you can then do stuff like manipulation on. We're not really focused in this work on manipulation, but just showing, can we do like contextual control of the humanoid where like the environment is kind of interesting and like, but we're not like focused on, oh, can we manipulate this or that object in the environment? So like, I think there's somewhat of like a philosophical difference, or like, the purpose of the work is different. It's not to say those works are better or worse than ours. It's just a different problem, I guess, in some way.
Yeah. Okay. I wanted to follow up on something.
You could combine the two kinds of approaches to learn like a general controller.
Right. How limiting do you think the height map input is to the policy? Because that ties into all this, right? Because like if you like part of the reason why it scales so well off of just a couple to 120 videos is probably
Yeah.
because the height map is a very, very good representation for this task, right? So like that is so how impactful do you think that is? Do you think you would need to move to something else later on, or what are your thoughts?
I think the height map is somewhat limiting for a few reasons. Like, one is that the resolution is reasonably low. It's like we were using like an 11 XL grid. So like, yeah, it's much lower resolution than something like a depth map. And the spatial resolution is also not that crazy. And it's a fairly small area around the robot. Like, if you see, like, that's kind of like what you're looking at in terms of like what it can see around it. So if you're going quite fast,
Gotcha. Yeah.
the amount of time, especially like the height map is somewhat delayed. So I think you could get better locomotive performance with a different representation, or with, yeah, that kind of thing, maybe direct from depth or RGB or something. So that's it definitely is possible that by changing the input condition, you could improve the performance of these policies. However, one thing I would say is a nice benefit that you get from the height map is like the input is like 360 natively. And because it's built from a LiDAR, we can also see behind the robot. And that means that, for example, like the sitting stuff, right, which just knows to use a single camera looking forward, especially if it's static and doesn't have any sort of active vision, you wouldn't be able to have the same range of behaviors. Yeah, so I guess there are kind of trade-offs. So you could maybe add more cameras or different stuff, but I would just note that also.
Right. But of course, if you have more cameras and have a larger input space, then you potentially need more examples. It depends, I guess. Yeah.
Yeah. And yeah, I mean, I don't think, though, there's any reason that you could not scale this to many more examples.
Yeah, absolutely. Makes sense.
Yeah.
I have one last question, or at least, I don't know, which was about, you'd mentioned at the very beginning that you often failed to convert videos into these 3D maps and go through the whole pipeline. How do you have an idea of how often it failed at the different steps?
I think I don't know exactly what our pass rate was, but I would say, like, from our own recorded videos, like, to like what we would use in training, it was somewhere between maybe 30 to 50%. I don't know exactly. But
that's pretty good. Yeah.
Okay. Yeah. It's not like,
right.
yeah, I don't think it's atrocious. Yeah, but it's not like amazing either. But from like internet videos, like we didn't use any internet videos in our training pipeline. Like, because it's just like the data quality is like a lot lower. Both like the reconstruction works worse, and it's surprisingly difficult to get like exactly what you want from internet videos. Yeah.
Interesting.
Even if you spend a lot of effort, like I know Hongsuk mentioned it before, but like our collaborator David spent a lot of time trying to
watching a lot of YouTube video.
Yeah, watching a lot of YouTube videos. Scraping, different things, but it's just extremely difficult to get like, the quality of data that you can just literally get from recording on your phone from scraping those sites. So yeah, which is interesting. That was not necessarily what I would have expected a priori, but I guess it's somewhat of a...
That's a very interesting point you point out, because like what you're saying is that the search cost of finding the right video, even though there's so much video, let's say on YouTube, is more than you just like taking up your iPhone, but then just take some video in a while, but you know what qualifies as quality video, and then that's just 1, 2, and that's enough.
And I think I guess like a priori for me it was surprising, but I think it was not as surprising as if you were in the field, because I think if you talk to people who work on like video malls or those sorts of things, I think I might be wrong about this, so take it with a grain of salt, but I think I've heard that, like, for example, for video malls, like the pass rate for those of internet videos is somewhere around like 1% or something. of the data scraped is actually used. If you think about like 1%, that's for everything that would go into a video model, which is already a much more diverse set than what we want in this project from that perspective. And obviously like they're using a much broader like net than we are, like types of searches and stuff. But yeah, it's interesting to consider it from that perspective as well. And that's aside from the fact that the reconstruction tools in practice do not get work as well on internet video as on just iPhone captured video for whatever reason. You know, other people would know more about why that is, like training, data mixture, etc. But empirically, that seems to be the case.
I do think we can somehow utilize the internet videos. I think the quality of the kinematic data is quite good enough, which just have like action-free just state. So as I first mentioned, if we don't have to use the like construction of the environment from internet videos, I mean, if we can just use the like joint angles, I think that those data already have some prior about the motion. It just doesn't have the physics, and which is important. Like I think we can find a somehow way of utilizing it. And I do think it's kind of a way to like scale up the like robotics action policy.
Yeah, so I guess like maybe as a final question, like usually sometimes we ask like, let's say if you guys have another, let's say 3 to 4 more months working on this paper, like what would be 1 or 2 additional thing you would want to push this research a bit further? Like would you collect, I don't know, more than those 120 videos? Would you 10x that, or would you spend more time?
I feel like collecting more videos is one thing. Like then also switching the height map condition to a depth condition would be one thing that I would try. I think height map is actually quite limiting for us. The LiDAR on the G1 is actually does not see right in front of the robot that well. So you're really relying on your LiDAR odometry for your reconstruction. Like because you only see like, the LiDAR only sees like 1.5 meters in front of the robot. So
that's why you said there's a lag.
Yeah. So that's one thing, is like just switching the condition and scaling. Obviously just spending more time tuning the policy. The project at the end came together quite quickly. So I think you could get better motions and different things like that. Yeah. Yeah, maybe Hongsuk has some different answers.
I mean, I think like it's always interesting to show like cool demo, especially for this type of projects. So I think I would work on like some kind of dynamic motion, as we talked about, like jumping between stepstones and like doing parkour. And for those aspects, I think we need better, like fundamentally better reconstruction of both environment and the human. And I think there's not much thing to do for the reconstruction, to be honest, of the environment. But like for the human, like I talked about like translation of dynamic human point cloud. I have some way of like I have some idea of solving it. So I might work on it and then like collect such like dynamic data.
I had one other question. Sorry, that just came to mind because you were playing those videos. I like all these directions, but why does it walk around like it's a little bit drunk? Why is it like staggering with its chest and its arms out to the side like that?
That's actually basically my fault, because
Arthur walks like that. He walks with a swagger, maybe.
Maybe a bit, but not that much. Yeah, basically, in the policy that we use to record these videos, I actually like overcooked the domain randomization in Sim by quite a bit. And so basically I was pushing the robot way too much. And so I kind of learned these poses that are maximally like, have the maximal, I think like, angular inertia basically. The next day I actually did like a fine tune with like lower domain randomization. And this issue was largely alleviated, but we did a lot of our recording on that day. So that was, yeah, maybe at some point we should go back and...
All right, makes sense.
Yeah.
Well, okay, cool. I mean, maybe as one final question, is there any papers that you guys come across recently that you guys want to give a shout out to? Doesn't have to be locomotion or like video, But anything that you think is quite pique your interest,
I found the like human diffusion controller from probably Peking University. Like it is like kind of applying the like diffusion forcing on the actual humanoid, G1. Like I guess Allshire would agree. Like we are interested in coming up with like better architecture and advanced ML theory to like have like better expressivity on the motion and behavior.
Arthur, do you have any
Oh yeah.
papers?
I guess the the probably the paper that I read recently that was the most interesting was one that is about to come out from one of our collaborators on this paper, which I hopefully pretty sure by the time this podcast comes out should be public. But basically, I think Hongsuk is also enrolled in that project where they basically do optimization of flow, like flow-based robot policies with a PPO-like objective, and I think it's just a really clean reframing of the problem of policy learning with a different kind of model, but still using basically the bones of like the PPO algorithm.
Pretty cool. I'll have to keep an eye out for that.
Yeah,
when it
I'll
becomes
send a
public.
link when it's out.
Okay,
Yeah,
thanks.
for
Sounds
sure.
good.
Okay, all right. Well, I mean, thanks you so much for making the time, guys.
Yeah.
I thought it was really, really cool work.
Yeah.
I didn't quite believe that this can be done now, but I mean, you guys have the videos to show for it. Yeah, cool. So and nice website again. Like I think that's the reason why other projects are copying the website style. But no, it's really refreshing. I really like all the video demos. Like it's not like crazy parkourish, but then I just knowing that these all just come from a bunch of like videos that you take from iPhone.
Yeah.
I mean, I'm not a researcher, right? So I look at things very layman, but I just like this whole pipeline. I just feel like, oh, okay, I think maybe the tech is there. It makes it a lot more accessible.
Yeah.
Yeah, to train these things. Yeah, cool. Well, okay, thank you so much. All right, Chris, what have you learned?
Hey, yeah, I really liked this paper. I thought it was really cool. I mean, for me, I was like blown away by the fact that you could even do this kind of reconstruction just from monocular video, to be honest. Like that you can generate these 3D maps that you can simulate robots in, and
yeah, the computer vision part, man.
Yeah.
I guess you're talking about the computer vision part, especially the real to scene part, where from a simple video you have a 4D thing, from a monocular normal video, right? Yeah, it's pretty amazing. Like the computer vision, the advancement over there. But I mean, I think also like they said, like in a way, you can maybe the real to scene part, you can, to your point, also like they can start off with something that also come with depth. Like it doesn't have to be just but the rest of the pipeline is still interesting, I think.
Definitely.
Right?
I'd say it's all interesting. Yeah, it's definitely like if you can figure out how to scale it off of like lots of videos, like like there's so much more monocular video in the world than there are like iPhone RGBD or videos, right? But
yeah, I mean, it seems to me that like so maybe the other way to do this is you just to simulate a lot of different environment, right?
Yeah.
But I guess because the world is already so diverse as it is, you just jack out your phone. Probably every place you point to is a unique environment, right? I mean, there's no exact same staircase anywhere in the world, right? All the staircases are slightly different, maybe, let's say. So, I think it just allows more so than, I don't know, in my mind, maybe more so than capturing what the human would do I guess it's a combination of both, right? How the human will react given the specific environment they're in. And so, and video is just such an easy way to capture both. I was a bit mind blown that they only take 100 video or so to get to a policy that, that is quite, like they say, context aware. When the robot go backwards, it will just like go towards the bench and sit down on the bench. I thought that was okay, wow. You get that like pretty quickly with not a lot of video. So, but I wonder like how much more videos will give you, right? I suppose more very diverse video taken at a very diverse environment. Like, would you say so?
So I think
Um,
I think that there's this knob that makes it work better or worse base, which is like the input size. So I think the thing to remember was that the input size was this height map that was very small. It was like 11 by 11 or something, he said, right? And actually fairly limited. So my guess is that they actually wouldn't get a ton of, this was my read of it, was that they wouldn't get a ton of extra quality from just purely scaling what they currently have. But that Arthur would really, but they would need to scale to like using the depth cameras to like really take a lot of advantage. This is just a guess, obviously, but like one of the things that you can do with that like relatively small input space is that I'm sure that they like actually can saturate it pretty well with all the different environments and stuff that they've seen in those clips because it's such a small and well structured input. But like to really take advantage of this, my guess is they need a lot more. They would still need to scale data, but I don't know.
Well, but so what you're saying is that because of the height map that they have, they're using it right now at test time is only about say 1.5 meter, less than 2 meters, right?
Yeah.
But would you not say that is also the effective, like let's say, how should I put it, effective space that a humanoid can maneuver anyway? So anything further,
yeah. But it was also
like,
lagging, right? It's slow. It's so like there's a whole bunch of things that because this was because of the input from the camera from the lidar on the head. So like my guess is like just the space of things that thing can support is probably fairly small. So like so they mentioned like doing parkour, right? So like for that one, you probably need a depth camera, which is getting very fast inputs and fairly rich. So you can like figure out where to like place the next foot so you can look further ahead, right? So like, cause like, especially if you want to have it leap, right? Like you can't leap if you're constrained to this little box around the robot's feet. So none of these are methodological issues. They're issues basically just with like what the robot has, I guess, right? So like nothing that you couldn't easily extend the paper to do, I think, from my read, right? That was I don't know.
Cool.
Yeah.
Yeah, there's all these like really cool papers with like especially with the Uni 3G ones. There's so many of them with cool demos like coming like week
This
after
was one of
week.
the ones that just blew me away though. Like I think we had like a run of like three of the Robo Papers episodes where the authors, when we asked at the end which paper they liked recently, was this one. It's like
no, they did a great job with the actually the quality of the video that they use in the video demos. I think I think they were quite humble, being like, it was a quick one, but it's well done, I think.
Very nice.
And of course, like done in Berkeley, like it's my favorite place, so so it's good. It's good to see a very, very familiar environments or sceneries. Okay, cool. Anyway, until the next one, I guess. Sorry, Chris.
Did you have any final thoughts? Anything? What did you think?
I guess my final thought is, there are some papers that is quite clear that they are on some trajectory in terms of lines of research, where you think, okay, maybe there's a scaling angle somewhere, where or maybe you add a bit more compute and then things will change. Maybe qualitatively speaking as well. This one, I'm still trying to get a sense because they already get something going without not much. 100 video, these things run real time. The videos are easy to get. So, this one I'm not too sure what would be like. Can I imagine another 10 other papers that will follow this line of research and do more? I'm not. Yeah, I don't know. This one I'm not too certain yet. Yeah. Because you see, right? I mean, one of the I think I kind of asked that question as well. Like one of the big school of thoughts about using video data is, there's so much video data already on YouTube, right? So, but you listen to them talk, like they try to script and they also didn't use the video from YouTube. So it's like, okay, then maybe the benefit of at least one of the benefit of why people want to use video data is because you can get them. They already exist on YouTube. So maybe the YouTube data is not that useful. Even though we have so much of it. Like just seething out to find the right clip to use, it's so much work. Might as well just take some video. I mean, having said that,
Yeah.
taking this video over 1-2 days, like 120 video is trivial as
It's
well.
really not bad. Yeah.
Yeah.
Yeah,
so
that is
maybe
kind of my fear about
Mhm.
YouTube videos as well. They're just not going to end up being very useful, but we'll see. Yeah.
Interesting. Interesting.
Yeah.
Yeah, it seems to be that one is a search cost, right? You need to have a very good video embedding search kind of thing to find the right video clip that exactly like match all the things that you want in, before you can. So the curation step it's a big step, I think, for them. Whereas in this case, if you know what you exactly need, I imagine the human, the main human character needs to be somewhere in the middle of the frame. You don't move your camera too much. And you set up that way, good lighting and all that. Yeah.
Right. Like YouTube videos are video as a communication medium, right? Like, which is actually fundamentally different from what a robot's doing. This is my feeling on this, right? Like, because like for a robot, like a lot of the data, a lot of the video that you find useful is maybe kind of boring as a YouTube video. Like it's not like there's no cuts, there's no scene, there's no angle changes because your head's where it is. You see, right? Like it's got to observe enough of the scene to be valuable. It's just like it's optimizing for something fundamentally different from robots, and I have trouble wrapping my head around whether or not that would actually be useful. Like,
well, but I think you're talking about, let's say, 0.1% of all the YouTube video on
that's
YouTube,
right.
though.
So you have to find those.
That you see.
Yeah.
I think 99% of the videos, like, they are not entertaining. Even some people try, but they're just not entertaining. And then, but those are the, let's say, mundane video, or just some live streams of some dudes doing some stuff, doing parkour, let's say, for hours. I mean, no fancy editing, but fixed camera, maybe just doing some live stream.
So that actually would be useful. Right. Like, okay,
there are a ton of video like this on YouTube, right? So I think it's just a matter of finding searching in this huge data set called YouTube. I think the search cost is the difficult part. My gut feel is that there's actually a lot of these so-called boring, but then maybe somewhat useful video for robotic learning that is somewhere on YouTube. Yeah. But it's hard to find the right feed, because it could be maybe it's a 10-minute video, but only the 1 minute of it is good, right? So you kind of have to find at the frame level almost, or at the scene level. And so, but then you get to the question is where, like, does it make sense to run that search because it's compute, right?
But then there are lifetimes of video uploaded like every day, right? Like it's much video to search through.
I read somewhere like every day that at least like 3 to 4 million videos a day, or maybe even more than that now, on YouTube. Right, each video is at least a few minutes long, average, let's say. So it's a lot of data going in onto YouTube. So the good thing is that we have this huge archive. Okay, I think the other question is that right now, presumably only like Google or DeepMind have access to that, unless scripting that is also non-trivial, right? Because presumably you need to script the whole thing before you can even do the search. So anyway, maybe it's just a lot more tractable to just yank up your iPhone and take specific video, which is what they've done here. And they get the result a lot sooner.
Cool.
Yeah,
it's a cool paper.
Okay. Cool. All right, cool. We'll
see you.
Talk more next time. All right, cool.
See you next time. Bye.
All right, see ya.